Okay, so as you go over the study guide for exam 5, there are a couple of things that I need to tell you that you don't already know, and then we want to review some things that are both on the guide that you need to know, and then a few things that are just from previous units that you also want to make sure you review. The first one is we talked about the definition of period, which is the length of time required to complete one cycle. And we want to introduce another quantity called frequency. And the relationship between period and frequency is that they're reciprocals of each other. And that's pretty evident if you look at the units, right? Period, by definition, is the number of seconds to complete one cycle, or any time unit, but usually seconds. And then frequency is, we flip that. It's how many cycles there are per second. And because we didn't want to keep saying cycles per second, we named a unit hertz that is equivalent to how many cycles per second. And so if period is 1 over frequency, then frequency is 1 over period. So you can determine one from the other when given. And then also just reminding you that the moment of inertia, or the rotational inertia of an object, is proportional to mr squared, which means that two factors must be considered, both the mass, but then more importantly, where that mass is located, as in how far away from the axis of rotation the mass is, because that quantity gets squared. And this is why we saw that the disk made it down to the end of the incline faster, because it had a smaller rotational inertia, and so it was easier to start and stop rotating, whereas the ring, with all its mass on the outside edges, caused it to be more difficult to start and stop rotating. All right, and then there's this notion of angular velocity. And so imagine this object. I used the example of horses on a merry-go-round on the review, but if any object goes in a circular path like this, you could talk about how its angle changed. And just from this picture, you can see that the position of this object changed 90 degrees, or half pi radians, as it went 1/4 of the way through rotation. And so the question is, if I compare that to an object that was closer to the center, like again the horse on the inside of the merry-go-round, what do you notice about their angular velocities? Well, during the same time period, they're going to go through the same angle. They're both going to go through 90 degrees, and it's going to take them the same amount of time because they're fixed on the platform. And so you can notice that both the inside and outside horses have the same angular velocity. But then you can also notice from the picture that the green path is longer. And so if both of these trips take the same amount of time, they'll have different linear velocities, even though their angular velocity is the same. And so how can we relate these two quantities? Well, we have an equation that you won't have to do any math with this on the exam, but the linear velocity is equal to the angular velocity times the radius, right? So for the merry-go-round, the two horses are going the same angular velocity. They're going to go around the same number of times, but the horse with the greater radius has to go through a bigger circle, and so it's going to have to go faster to make it around the same number of times. And then I ask about the roller coaster. Consider the top of the loop. When you're at the top of the loop, you have two forces acting on you. mg, of course, pointing towards the center of planet Earth, called down. Normal, also down. And that's what keeps you in your seat, right? Again, the reason you don't fall out of your seat is not because there's anything pushing you up per se, but because you want to travel in a line tangent to the circle. You want to go flying off to the left in this picture, and as a result, the roller coaster pushes down on you to keep you in your seat. And then what did we talk about? We talked about how the normal force gives you your apparent weight. So the harder the normal force pushes on you, the heavier you feel. And in this case, with a very small normal force, because gravity is helping pull you in the circle, right? It's contributing to the centripetal force. Then you feel light at the top of the loop. When you get down to the bottom, of course, mg is still acting down, and normal now is acting up, but the question is it smaller than, equal to, or larger than mg? Well, think about it for a second. Is there an acceleration at the bottom of the loop as you either enter or leave the loop? And the answer is yes, because you're changing direction. What kind of acceleration? Centripetal acceleration, right? Directed towards the center. And so if there's an acceleration towards the center, there has to be an unbalanced force towards the center. And so the normal force must be larger than the gravitational force, which accounts for that acceleration towards the center as it changes your direction and pushes you into the middle. And that's why as you enter into the loop, right, if you're trying to hold your hands up, it's really hard to do it as you start and finish the loop because of that huge normal force on your body. You're going to feel heavy, and you're having to push your arms into the middle of the circle and cause them to accelerate centripetally. All right, so then let's turn our attention now to some momentum review. Notice that on that study guide I gave you in class, we mentioned we didn't go back and do momentum and energy, but those will, of course, be on the exam. And so here's a couple of examples that we worked. It said a 6 kilogram ball is traveling 3 meters per second east when it collides with a 4 kilogram ball initially at rest. If the balls stick together, how much energy was lost in the collision? So I started off with a bit of a difficult question, right? In other words, I'm kind of baiting you to say that no energy is lost, but you should recognize, if you go back and review the types of collisions, these things stick together, and so they're going to have the same final velocity. And remember, we have a special term for that. We call that perfectly or totally inelastic. And inelastic, of course, by definition, means that there's some kinetic energy lost. And so we are going to have to do some math in order to answer this question. It's not just the easy, obvious answer of 0 that somebody might want to put. All right, but in order to find out how much energy is lost, we need to find out how fast they're going together. And that's a question of momentum, right? Because linear momentum is conserved. And here's that equation again. If it's a closed system, which all of your systems on the exam will be closed, the total momentum before has to equal the total momentum after, which for a two-object system looks like this. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And so now I just plug in values. Recognizing that they both have the same final velocity, I can just add their masses after the collision. And so 6 times 3 plus 4 times 0 before gives 18 kilogram meters per second of momentum before. And then after, they have a combined mass of 10, and we're looking for their final velocity together. And so 18 equals 10v. And so together they move off at 1.8 meters per second. Now that I know how fast they're going, now I can turn my attention to the energy to find out how much energy was lost in the collision. So I use my kinetic energy equation, 1/2 mv squared, and I plug in the values. I know that before the collision, the 6 kilogram ball had 27 joules of kinetic energy because of 1/2 mv squared. The 4 kilogram ball did not have any because it was at rest. And then after the collision, I know that together they had a combined mass of 10 and a velocity of 1.8, and so their kinetic energy was 1/2 of 10 times 1.2 squared, which is 16.2, and you can see that 10.8 joules of energy was lost. Where did it go? It could be sound, it could be heating, it could be deformation, any number of things. All right, here's another one. A 5 kilogram ball is traveling west at 2 meters per second when it collides with a 5 kilogram ball at rest. If the collision stops the first ball, what is the final velocity of the second ball? Again, we have a question of conservation of momentum. So I go with that same equation. The total momentum before equals the total momentum after. The two objects stay separate, and so they're going to have different final velocities, but I know one of them, so I can just plug those in. 5 times 2 plus 0 for the first before the collision, and then 0 plus 5 times v for after the collision. And then recognize that the second ball must be going 2 meters per second. And then, because I asked for the final velocity, we need to make sure we have a direction. And I didn't explicitly state it, but here I'm working with the positive direction being west. And since my final answer was positive, then I know that it's moving 2 meters per second to the west. And that makes sense too, because the momentum before the collision was to the west, and so the momentum after the collision must still be to the west. And then if I were to find the kinetic energies, to find out what type of collision this was. You can recognize pretty quickly they have the same m and the same v before and after, and so the kinetic energies before and after will be equal. And whenever kinetic energy is conserved, which doesn't happen frequently, but when it is, we call that elastic. And so this is an elastic collision. All right. An 8 kilogram ball at rest struck by a 12 kilogram ball moving 3 meters per second north. If the final velocity of the 12 kilogram ball is 0.5 meters per second north, what is the final velocity of the 8 kilogram ball? Exact same approach. I just plug into my formula, give the values, and get a final answer of 3.75 meters per second north. And then if I want to know what type of collision it is, I'm going to plug into the kinetic energy formula. And notice that kinetic energy was gained, and so there was some kind of explosion or some kind of spring that was released, or one of the balls was somehow elastic and had energy stored in it, so that the system gained kinetic energy, and so I would call that a super elastic collision. And for all these, you can go back and work the momentum practice problems that I had online that you worked several weeks ago through the Google form. That's where you can access it and to get more practice if you need it. All right, and then finally we did a quick review of energy. Of course, we've learned of 2 types of mechanical energy so far, gravitational potential energy and kinetic energy. And remember, at the honors level, we're just going to assume the Earth is involved in the system, and so gravitational potential energy is there, and it's relative to the floor or the ground, whatever the lowest point in the frame of reference is. And so in this case, I have a 4 kilogram box at rest on a 2 meter high table, and the question is, how much total energy does it have? Well, does it have gravitational potential energy relative to the bottom of the floor? Yes. Does it have kinetic energy? No, because it's not moving. I can use my equation for gravitational potential, mg times the height, or the change in y, which in this case is 2, and I find that it has 80 joules of total energy. And then I say, well, what if it wasn't at rest? What if it was moving to the right 2 meters per second? Now how much total energy does it have? Well, it's at the same height relative to the floor, and so it's still going to have 80 joules of potential, but now it also has kinetic. And, oh, I forgot the squared there. Obviously, kinetic energy is 1/2 mv squared. Plugging in the values, I get 8 joules of kinetic, and it already has the 80 joules of potential, and so that gives it a total energy of 88 joules. So then what if it continues going 2 meters per second as it slides off the table and then hits the ground? The question might be, how fast is it going when it hits the ground? Now, could you use kinematics? Sure, because once it leaves the table, there's going to be a constant acceleration. But we already have the total energy, so let's use that. If there's not any air resistance or any friction on the table, then it's not going to lose any energy. And so how much total energy will it have right before it hits the ground? 88 joules. And right before it hits the ground, what will its height be? 0. And so therefore, how much potential will it still have? 0. And so the total energy will be 88 joules still, but it will all be kinetic. And if kinetic energy is 88 joules and its mass is 4, I can solve for its velocity, which I believe I remember is like 6.7 meters per second. All right, so again, look over your notes, all your old stuff, practice problems, old quizzes, everything, and let me know if you have any questions. All right, good luck.